Helmut Neukrichen is 43 years old and born and educated in Germany. He grew up in Krefeld, which is close to Düsseldorf. He studied computer science in the most western city of Germany at the Technical University of Aachen. His focus there was distributed systems and software construction. There he graduated in the year 1999 with a Diplom Informatiker degree which is comparable to the MSc degree in computer science. In 2000, Helmut started his PhD studies at the University of Lübeck, where he was employed as a research assistant in a project funded by the 5th Framework Programme of the European Community. In 2003, Helmut followed his co-supervisor to the University of Göttingen, where he finished his PhD thesis in 2004. While Helmut was finalizing his PhD thesis, his wife was an exchange student at Landspítali University Hospital. This is how they both got to know and love Iceland. After his PhD, Helmut started as a postdoc in Göttingen, where he was then vice leader of the Software Engineering for Distributed System Research Group, and in 2008, Helmut became first assistant professor and then associate professor for computer science and software engineering at the University of Iceland. Coming from Germany, Helmut has many internal contacts and collaborations, not only concerning research, together with universities and industry partners abroad, but also on an educational level, such as inviting and being guest teacher or serving as a contact point for student exchange between Germany and Iceland. And he's an avid promoter for Iceland in interviews and interviewing partners and in German media. Helmut strives to promote the Iceland and the University of Iceland abroad, and he's on the other side a very good candidate for that. Helmut served as a reviewer for various scientific journals such as the IEEE software conferences and books, as well as for certifications for the German Software Testing Board. His research contributes to the European and international standards, and Helmut participated in the standardization bodies of ITU-T, which is the telecommunication standardization sector of the International Telecommunication Union, and ETSI, which is the European Telecommunication Standard Institute. The corresponding standards to which Helmut contributes are used by major industry partners and players such as Ericsson, Siemens, Bosch, and Porsche. They use them to specify and test distributed systems such as the 4G mobile telephone system or electronic control units in cars. Helmut is teaching here at the University of Iceland together with his research, and has taught in 6 different courses and has so far supervised 19 MSc theses and was co-supervisor or in the thesis committee of 4 PhD students. Helmut's publications are in international scientific journals and more than 30 peer-reviewed papers at international conferences, but the publication tradition in computer science and software engineering are slightly different than elsewhere, where the even stricter acceptance rates for these conferences are compared to some of the journals that traditionally are published in. And the reason for this is because the innovation cycle is so short in this field, and the fast-track conferences are more preferred and appreciated as a publication channel. Helmut is successful in acquiring funding for both teaching and research from Icelandic funding, and as well as in the European level and international. He has successfully secured 25 million kronas recently for a future PhD student. The funding comes from Nordforsk to set up a Nordic Center for Excellence. On a personal side, Helmut loves to ride bicycle. His wife is a medical doctor now at the Heilsugæslan, and together they have 3 kids. Helmut's research fields, as we said, are in software engineering and distributed systems, and we will now have the pleasure to hear him give a lecture about his past, current, and future research. On a more personal note, Helmut is a good example of the foreign talents that the University of Iceland now has access to. The the rate of this is growing, has reached that level now that 1/4 of our academic staff is from abroad. And I think with Helmut's lecture, I now declare that this is not an issue anymore. We can accept good talents and get good talents from wherever we like, and it's a good example of what is possible as the Iðnaðar, Véla og Tölvuverkfræði and Tölvufræði deild has now received this talent and show. Helmut, Herr Professor Dr. Helmut Neukrichen.
Thank you for the introduction, Hilmar. So it's nice to have you here to celebrate with me, and I'd like to use the next 30 minutes to give you an overview of my research. Part of it is about real-time systems. There you learn that you often use intervals to specify time span, so it may be 30 minutes plus minus 2 minutes, so don't get nervous if I'm already talking 31 minutes. 1 minute later I will be finished. So I'm talking about distributed systems, which essentially means you have hardware and software components that are located at network computers, and they can only communicate and coordinate the actions only just by passing messages. My other research field is software engineering. Oh, sorry, I have to switch, sorry. So, as said, I like to talk about software engineering and distributed systems. Distributed systems, as you heard, is hardware and software running on network computers. They can only communicate via messages. And software engineering is a pretty broad field, so I picked here as an example software testing, which is where I did most of my research in. And for example, you may want to test that some message M is correctly transmitted via a distributed system. For example, if a user Alice sends a message to both Bob and Charlie, the question is, how do you test this? To do so, you have to replace some of the components by so-called test components, like the ones of Alice, Bob, and Charlie, as you see here, and then you can use the test components to stimulate the system under test, like sending a message M at test component A, and then the other test components like B and C could then check whether they observe the expected result. And since these test components need to work together, they themselves need some coordination, like test component A should not send a message before B and C are ready to receive. Also B and C, they make local observations concerning the message that they did receive. However, you need to come up with a global test verdict, so they need to exchange information about this. So the test system itself is also a distributed system. You often have a main test component that coordinates them. So as you've seen, my research fields are both distributed systems and software engineering, and I think it's most exciting where these two fields meet. But as you will see, I do not only work in this intersection, but also in each of the fields separately. Hilmar already talked about my academic journey. So as I'm born in Germany, I was educated there, so I studied in Aachen computer science, then I started my PhD in Lübeck, finished it in Göttingen before I then went here to the University of Iceland. So in Aachen, this was in the time before the Bologna process, so no master degrees, but rather a Diplom Informatica degree, which was also already in the area of distributed systems. I did their work on service brokering by taking load information into account. And then in Lübeck, I worked in a European research project called Interval, Formal Design, Validation and Testing of Real-Time Telecommunication System, where in addition of the University of Lübeck, major players such as Ericsson and France Telecom were in the consortium. The software company Telelogic has since then been acquired by IBM Rational. There are smaller companies like Solinet and Teletel, and there's also the French research institute Verimac. The results of this project were then a huge part of what I wrote my PhD thesis about. The title is Languages, Tools and Patterns for the Specification of Distributed Real-Time Tests. And then later in 2008, I and my supervisor, we also wanted to promote the ideas from there, which were initially developed for telecommunication systems, to promote them also for being used in the automotive domain. So if you buy a car that has some electronic control unit, in particular if it's, for example, from Bosch, it's very likely that it's tested using ideas to which I contributed. So what are these ideas? So it was about, yes, specifying and testing distributed systems. There are some languages available that are used there, for example, message sequence charts, or short MSC, which is a graphical notation standardized, as we learned, by the telecommunication standardization sector of the International Telecommunication Union, or you rather prefer to call it ITUT. This is used for specifying systems, in particular the message exchange, and then for testing systems there's a language called Testing and Test Control Notation version 3, or short TTCN3, which is standardized by ETSI, the European Telecommunication Standards Institute. You know it maybe from the GSM mobile telephone system, which has been standardized there as well, and also for the current fourth generation and third generation. There also ETSI participated in this. And since I wanted my real-time extensions that I developed as part of my PhD studies make part of these standardized languages, I also worked in these standardization committees, which was some interesting experience. So what was it about? You see here such a message sequence chart, which consists of different instances. Each instance has an instance axis as some sort of lifeline, so you see the events that occur for that instance ordered from top to bottom. So for testing later on, we can then designate that a certain instance is what we want to test, the so-called system under test, and then the other instances serve then as interfaces of the testing. In the telecommunication domain, is also called service access point, SAP. So there's some ISAP interface via which we send some message to the system under test. And then we expect as a response to this message that the system under test sends then this mData indication message, which is then observed at the MSAP interface, and then according to the specification, then we need to send back some acknowledgement message using this mData request message. So this message exchange is essentially what you see here. These are these arrows. What you see as well is a construct to specify loops, so we expect this behavior that it occurs exactly 100 times. And then the real-time constructs that I then added to this graphical language are shown here. So with that one, you can specify that this periodic sending of this message should occur exactly every 10th of a second. A further requirement is the latency between sending the stimulus and then observing the response at the other interface. So this should be less than 10 milliseconds. You can then take such a message sequence chart, use it as a specification, and then implement something that is according to the specification. You may, however, also use it then for testing. Either you then manually derive tests using this message sequence chart, or this is what I did also as part of my PhD thesis. You can develop tools that automatically create test cases from these MSC specifications. And on the next slide, you see an example of such a TTCN3 test case, which is in this state a pure functional test case. This is what the language supported when I started my PhD thesis. So it looks like an ordinary programming language. So we have here this loop for testing this 100-time message exchange. You have the sending of the stimulus. You then specify that you expect to receive a message of a certain data type with a certain value at that MSAP interface. And then if you remember, we need to send back the acknowledgement to make the implementation that we are testing happy. And if we observe, in particular, this expected message 100 times, then we are happy, and we set then the test verdict to pass, so the system under test passed the test. So what I did then to be able to test real-time requirements, I developed a language extension which I called timed TTCN3. And what I defined there was the possibility to read the local clock of the test component where this is running. And since we want to have this periodic stimulus to send every 10th of a second message, we simply take the current time at a 10th of a second to it and use this then for scheduling when the next send event happens using this resume statement. We wait until this point in time is achieved, and then we continue execution by sending. Since we want to make this happen every 10th of a second, we take the last send time at a 10th of a second to it, and then the stimulus will be periodically sent. If you remember, there was also this second requirement concerning the latency. We already have the timestamp when we did send the stimulus. Now we need also a timestamp when we receive then the response. So we simply measure it then in this receive time variable. Now we have two variables containing the timestamps we are interested in. And then essentially we need to calculate the difference between these two to decide whether the implementation met the latency requirement or not. As part of my PhD thesis, I developed a library of evaluation functions where you simply have to pass in the timestamps and you pass in our lower and upper bounds. And this function then returns a test verdict based on whether this requirement was met or not. And there are so-called verdict overriding rules in TTCN3 which say once you did set the test verdict to fail, it will never be upgraded to pass again, even though if it later on in the end will be set to pass, it will remain fail if already the non-functional real-time requirement has been violated. So this was essentially what I did in my PhD thesis. After this, I stayed at the University of Göttingen as postdoc, where I did my independent research, also my independent teaching. I decided to teach agile methods, which I was interested in, and among others, I learned that a technique called refactoring is something that I found to be useful. This is about improving the internal structure of source code, cleaning it up, making it easier to understand. This is essentially what the definition of refactoring is, like changing software to make it easier to understand and cheaper to modify without changing the behavior. The idea is nothing new. This has been done for implementation languages such as Java already some time, but no one did it yet for the TTCN3 language. So I, together with a master student, we developed the first catalog of systematic TTCN3 refactorings. My experience from teaching refactoring is also that if it's not supported by a tool, no one will do this manually. So I felt that there's a need to have a TTCN3 refactoring tool. And it just happened that I talked to someone from the Motorola labs, what we are currently doing, and he said, okay, this is something interesting. We also want to work on this. So they contributed resources on developing a tool called T-Rex, the TTCN3 refactoring and metrics tool. While Motorola is nowadays not contributing to this tool anymore, I, at the University of Iceland, together with students and my former colleagues at the University of Göttingen with students, are still working on this open source tool. It's hosted on its own website, and it's now an 8-year-old tool. It's almost 100,000 lines of code. It's also a good example to use it as an object of teaching. So when I'm teaching the software maintenance class, then the students there have to work on this code base, which is a good experience for them. So to give you an impression how these TTCN3 refactorings look like, you see here some example TTCN3 code, and it makes use of so-called templates, which is what is used to specify test data. This is like constants in ordinary programming languages. But these TTCN3 templates, for example, they can also be parameterized. So instead of having just constant values like false for Boolean values, you can also pass in parameters that are then used within that test data specification. So you can pass in here some IP address, for example, as parameter. And then in your actual test behavior, where you maybe then send messages, you need to specify which test data you want to send. Then you simply refer to this template and pass in then some actual parameter value. Also, when you then are listening for incoming data, you want to check whether it matches the expected data. There again, you can refer to these templates with parameters. But as it is the case here, if you are using this template exactly this 2 times with 2 times the same parameter, you can maybe simplify this code. And this is then why you want to apply this inline template parameter refactoring, and the result is shown on the next slide. So here you see the refactored version, and what you see is that the parameter has been removed. Instead of referring to this formal parameter, we immediately use this fixed value, and then where it was referenced, we don't even need this parameter anymore. So if you have a look at the source code, it has been simplified. Of course, it may later then be the case that you again need a parameter. Then typically each refactoring has an inverse refactoring that allows you to easily introduce again a parameter. As said, my experience is you need to support it by tools. So this is how this T-Rex refactoring tool looks like. It's not only an ordinary editor, but, well, it can calculate metrics. It can point out problems, like that you should apply certain refactorings. And if you want to apply a refactoring, you can get a preview. So on the left-hand side, you see the code, how it looks like before the refactoring. On the right-hand side, how it looks like after the refactoring. So these are 2 examples of research projects that I did during my time in Germany. Then in 2008, I moved to the University of Iceland, first as assistant professor, then as associate professor, and now as full professor. And I teamed them up there with my new colleagues to use my expertise in quality metrics. There we had our former colleague Klaus Marius Hansen, who was working on software architecture. Christian Jonasson was contributing in statistics. So what we investigated was the correlation of software architecture and software quality as they are measured by metrics, so whether a good software architecture really contributes to good software quality. So what we found out that in general, if you, concerning the architecture metrics, if you avoid extremes, for example, if you consider the coupling of packages, you don't want to have a very high coupling, but you neither want to have a very low coupling, rather some balanced thing in between, typically correlates with good quality, as it's, for example, measured by simply counting the number of bugs that are reported for software. And we investigated there hundreds of open source projects for which we automated this analysis and found these correlations. Then I also continued work on refactoring, but I covered all that I could do for TTCN3 essentially, so I targeted a new language, namely the Unified Modeling Language, UML, which is just like this MSC example that we've seen, a graphical language. It consists of different diagram types. You probably know the class diagrams where you talk about the classes, which methods are contained in, how are the relationships between classes. And there are also so-called activity diagrams where you talk about activities or actions that are performed. They may get performed in parallel. You wait until they're finished, then you join together. And also there you may encounter diagrams which are pretty cluttered up because you have very low-level actions. Then you may decide that you want to merge two actions into one action, and this is this example of this merge actions refactoring. So this is the unrefactored version, and when you refactor them, you simply merge this action, which looks quite trivial here if you see just the graphical representation. But already just working with a graphical representation, you need to keep things in mind. So you need to check first, does this last action, the action 2, does it have more than just the connecting edge as incoming edge? If you would then join the two actions together, then you would change the behavior. This would then not be a refactoring anymore, because then the other incoming actions would also execute action 1, not only the last action 2. But if it's applicable, what you do then, you simply then take all the incoming edges of the first action, attach them to the second action. Maybe you want to have then the name for the merged node to convey the meaning of the both actions. So if you automate it, you simply concatenate maybe the name of the actions. And once you're done, you can then simply remove the connecting edge and can remove the first action. As said, my experience, you need to automate this with tools, otherwise people do not apply it manually. So when I wanted to automate this with tools, then, well, you need to be aware that you typically work with the diagrams, with the graphical representation, but whenever you have an UML editor, at least one that does more than just painting, then you have always what is called a UML model behind the scenes in the background, and this is one huge model that really contains information about all the elements, about all the classes, all the methods, all the actions that you have, and their relationship with each other. And then the diagrams only then visualize an aspect of them. There may be a class diagram which then still does not display all classes that are contained in the model, but only a certain package maybe is visualized there. So the diagrams are only just a part of what may be contained in the whole UML model. And if you have a look at related work that existed on refactoring UML, they only worked on the UML model. They completely ignored the diagrams. So this means after you changed the model, the diagrams were more or less useless. They were not in sync anymore with the model. They may refer to elements that did not exist anymore afterwards. So my approach, therefore, was for a refactoring tool, we need to refactor both the model together with the diagrams. And I used for this so-called model-to-model transformation languages. One example is QVTO, which stands for Query View Transformation Operational. And while it has been used to transform UML models, the new thing that I did was to consider also the diagrams as models, which is possible. And then you can use QVT not only for transforming the models, but also for transforming the diagrams, so you're able to keep these things in sync. I had then a master student who implemented this in a tool. Basically, this was a plugin for the open source UML editor called Papyrus. And this tool then essentially consists of a few hundred lines of Java code that essentially provides you some user interface menu entry to call a refactoring, and some code then to fetch then not only the UML model, but also the diagram from the Papyrus tool and feed it then into the QVTO transformations, which are then just a few hundred lines of QVTO, approximately 100 lines per refactoring, which is pretty short. Comparing this to the TTCN3 refactoring tool that I implemented together with students, there each refactoring is several thousand lines of code, mainly because it was done low level with Java implementation, not with this high level model-to-model transformation languages. The QVTO interpreter that takes then the models as input and transforms then the interpreter that we used at that time, it did not support the full QVTO standard, so there were some things that are in principle possible to do with the QVTO language which was not supported. To be able to do this, we needed to call some external helper functions. This is what this Java black box library is about, which is, however, just a few lines of Java code. And then once all these, the models and the diagram have been transformed, you can then simply return it, save it to the files that Papyrus uses, and Papyrus then simply then redisplay the refactored UML. A further field in which I was working on was e-science. So e-science essentially means you support science using computers, in particular if you have computational intensive science. Then your local desktop workstation is maybe not powerful enough for this, then you need some distributed environment to have more computing power available, like a cluster. And what you do typically is some sort of so-called scientific workflow. So you couple different tools together, so the output of one tool is fed as input to another tool, which again, some tools may run in parallel, then you have to wait for all to finish, you have to join them the results. Others are more sequentially, so you may have different workflows depending on what you need to do and depending on the tools that you are using. If your local distributed environment, let's say some computing cluster, is not even powerful enough for your problem, then you may need to use another cluster from some other organization that works together with you. This is then what grid computing is about. However, then you face the problem of heterogeneity. Every cluster may use different hardware. Even if the hardware is the same, they may use different operating system versions. They have different software packages installed. You need a certain library, however, that is not available on the other cluster. So these are problems that you are facing in grid computing. And I wanted to investigate then also, since grid computing is a distributed setup, I wanted to investigate, yes, in how far is TTCN3 applicable to do testing in grid computing. There I tested workflows which worked out fine. Some other more newer buzzword than grid computing is cloud computing. So it's about using computational resources on demand. So on one day you need maybe one CPU, the next day you need 10 CPUs, then you can simply request them from a cloud provider and get them. And since these resources are typically not available locally, you access these then via a network. You've seen on the introductory slides, networks are visualized often as clouds, so this is why it's called cloud computing. And as said, you can simply scale on demand. If you need more CPUs, you simply request them, and you pay per use. Typically, you pay per CPU hour, so using one CPU for 100 hours costs the same as using 100 CPU for 1 hour, just that you will finish much earlier. Furthermore, you do not need to invest into your own hardware. This is why cloud computing is very popular for startups. And in contrast to grid computing, cloud computing has not the problem of this heterogeneity because it's based on virtualization technologies. So even if the hardware is different, on top run virtual machines that provide you the same feeling, even though the hardware below may be different. And typically, cloud computing is cheaper as you can do it on your own. So it's typically just the economy of scale. These cloud computing providers, they have a lot of machines. They can get better prices than you will be able to get. In 2010, cloud computing was already so popular that it was something to investigate. So there was a project funded by the Nordic Data Grid Facility called NEON, Northern Europe Cloud Computing. And the idea was simply to evaluate whether the use of cloud computing resources is something that is interesting for e-science that is done at universities or academic research centers. So we simply used some pilot projects where we had some e-science projects and tried out how it feels to run them on the cloud. You can distinguish commercial public cloud providers like Amazon. At that time, these were already mature enough to use them. But you could also, if you want to enable this cloud technology also with your local resources so that others can use them on demand, you could set up cloud stacks on your own local machines. At that time, these were not that mature. This was the result of this research project. I then also investigated, again, is TTCN3 applicable in the cloud domain? What is different there, for example, with respect to grid computing, is that it's highly dynamic. If you request a resource like a CPU node, you don't know in advance which IP address you will get. So you need to make your test cases configurable at runtime just after you created a node. Then you know the IP address of some node that the test component has to talk to. So you need to enable a runtime configuration of the tests. The most recent buzzword is mainly big data, so it means it's essentially all kind of data that is too large to process it using conventional methods like your Oracle SQL database. Other people say everything that does not fit into an Excel sheet is big data. And to illustrate what the problem is with big data, I just want to have a look at classical cluster computing. There you have many very powerful CPU boards, and typically you have then some central storage, which is also very powerful, but it's connected then via some network to these CPUs, and the processing works then simply in a way that you move the data that is stored on the central storage, the data that you want to process, you move it via this network to the CPU, and with the big data this can be a bottleneck. And those alternative approaches that promise to solve these big data problems, like for example MapReduce, which is used by Google, there's an open source implementation called Hadoop available. They don't use the central storage, but they rather use a distributed storage. For example, Hadoop comes with the Hadoop distributed file system, HDFS. And there typically standard PCs are used instead of expensive server hardware. These anyway have hard disks, and what you do then is that on the hard disk of each PC you store a part of the data. And what you can do then, if you anyway have the data or a part of the data locally available, you do the processing exactly there where the data is stored. So this then means you move the processing rather to where the data is, and this may then help you to avoid this bottleneck that you have if you would instead move the data to the CPUs. So I did a research project in the domain of high energy physics where I wanted to know whether MapReduce is better than what is currently used there. For example, at the Large Hadron Collider LHC at CERN, the kind of e-science, the kind of computer-based analysis that they do there is based on a C++ library called Root, which has been grown for decades, which provides helper functions for doing the typical analysis. And they already have support for executing this in parallel. There's the so-called parallel root facility, short proof, which also comes with a distributed file system called Scala. And at CERN, they create petabytes of data each year, so this qualifies as a big data problem. So yes, I thought it's worthwhile to use Hadoop together with the HDFS distributed file system there. And since we are not part of the CERN collaboration, we are not allowed to use any of the real analyzers that are used there, but we got some sample analysis which is comparable to the kind of analysis that is done at CERN. We got it from the Max Planck Institute for Nuclear Physics in Heidelberg. And initially, I had the idea to use the Nordic high-performance computing cluster that we have here in Iceland, a very powerful cluster, but it uses, again, the central storage approach, so we were not able to install the distributed file system there. What we used then instead was cloud computing resources that allowed us to set up a cluster exactly as we needed with local storage, and there we then had, of course, the problem that these are commercial cloud resources which we had to pay, but luckily we got a research grant from Amazon so that we could use their Amazon Elastic Cloud. And in this environment we did set up this classical proof plus the distributed Scala file system, and for comparison Hadoop with the HDFS file system. And then we did measurements doing the same kinds of analysis, and you see here in this chart, you see on the one hand how it scales. So horizontally you see we add the number of nodes, and in the vertical axis you see the performance, the number of events that are processed per second. So it's almost linearly, so this scales very well. The bad news is that Hadoop, which is the red plot, this is slower. This delivers less events per second that are processed than the proof-based solution. And the reason, I think, is that we have a lot of overhead because of language mismatch. Hadoop is implemented in Java. I said the analyzers that the physicists do, these are implemented in C++. They use this root library. And then we have to do conversions between Java and C++, and this simply takes a lot of time. There are nevertheless also some good sides. So Hadoop together with HDFS is more fault tolerant than proof. So if node fails, Hadoop and HDFS automatically take care that jobs are restarted, the data is replicated. Also, it's a more widespread general purpose approach, so the physicists said they would be happy that it's easier to find personnel that knows about Hadoop than with the specialized proof thing. And another advantage is the network load, which is shown here on the right-hand side in the plot. You see the network traffic that is produced because of non-local processing. So the green line is the proof one with this distributed file system Scala, and there some significant network traffic is generated because not all processing is done at the nodes where the data is stored. In contrast, in our Hadoop-based solution, the network traffic is almost zero because we exploit the locality very much. But the reason why this does not show in the performance is that the analyses that were done are pretty much CPU intensive, so the network traffic, this is not really relevant. This does not contribute very much. It's rather this Java overhead that kills us here. So finally, I like to give you an outlook on some research project that just started. It's called eScience Tools for Investigating Climate Change at High Northern Latitudes, or short ESTIC. This is funded by Nordforsk. It's a so-called Nordic Center of Excellence. The project runs for 5 years. 13 research group, mainly climate research from all Nordic countries, participate in this project, and I here together with EBA, we secured 25 million Icelandic kroners funding mainly for a PhD student. I like to use here the opportunity to advertise that we are looking for a PhD student, so if you know good candidates, please contact me. And what is this project about? It's about the fact that these different climate research institutes, they all have different what is called Earth system models that model certain aspects of climate, like this EC Earth model that is used at the Danish Meteorological Institute, for example. It's able to give outputs concerning the precipitation and temperature change. And then there are models that model the ice sheet of Greenland, for example. And of course, if you have snowfall, this contributes then to the ice sheet. On the other hand, if the temperature rises, the ice melts and you create fresh water. So this output of the EC Earth model is some input that is very relevant for the other climate models. And then in turn, the output of the other climate models, like if the topology changes or fresh water is created, this then in turn influences again like Earth models like this EC Earth models. And where we as University of Iceland want to contribute to is in the coupling of these models. So the idea or the hope is that the workflow tools that we know from grid computing, that they help us in connecting these different Earth system models together. So that's the end of the presentation. I'd like to thank you. Thank you for your attention, but also I'd like to thank all that accompanied and supported me during my academic journey. These are my teachers and supervisors. These are former and current colleagues, not only academic, but also the administrative colleagues. These are students that did a lot of the implementation work on which my research was based on. Of course, also research partners in industry and other academic institutions, friends, my family, my wife, my 3 kids, and my parents in particular, and anyone that I forgot to mention. Thank you.
You certainly add Punktlichkeit to the group, Helmut. This opens up for questions, and I traditionally say this is the last time to actually barbecue with some intense.
Yes.
From now on, you're a professor, so this is the last time we can put you on the heat. I get the pleasure to start. So the first question I have, now you decided to stay here for some time. You looked at the environment, and you have some industrial partners in Germany. So who are your partners, and are there any possible partners in Iceland that you would like to work with or you see opportunities with?
Well, yes, like testing distributed systems, this is something that telecommunication companies do. So I was in contact with Simon and presented them my work, and they then said they are not doing this kind, even though telecommunication operators that I know in Germany, they are also doing testing. Simon said they rather rely on that the things that they buy, that they work. But, well, this was just after I arrived, shortly after the crisis. Maybe at that time any research budget there was very low. So maybe this has changed since then, so it may be worthwhile to ask them again. Also, I talked to CCP. They rather use their users as guinea pigs for the testing, so they don't use an artificial test environment, but rather while the users are playing their games, they are subject of testing, so they neither were interested in this. But yes, I think now, since the crisis is over, I think it's worthwhile to talk again with the bigger companies, because this TTCN3 testing, this is something which is of interest for big company like Ericsson decided to do all the testing worldwide with TTCN3. Also Siemens is using it. So it might be two heavyweight things for smaller companies, which we mainly have here in Iceland, but there are of course also bigger ones, so it might be worthwhile to talk to them.
Question from the group. You mentioned big data from eScience. A lot of people here.
Yes, I just attended a talk from Decode, so they also have big data problem. They have a lot of probes nowadays that they even can afford to analyze now, but if they would do so, they would have a lot of data. Currently, they're using this classic cluster setup. They talked about performance problems, so I was also in contact with them to suggest them to use big data. Yes, so this is also a potential partner. Yeah.
Questions from the group?
This PhD position, is it being advertised?
Yes, yes.
How long ago?
I think 4 weeks ago.
When is the deadline?
So the deadline was already, and we got the applications that we got that were not that satisfying, so we are considering to re-advertise it again.
And you advertise for computer science student or?
Yes, or related fields. And yes, we got applications from this Earth sciences, but there are already a lot of Earth scientists in this project, so we need rather computer scientists in this project.
So a question about the workflow system you were describing. You originally developed it for a grid system, then you tried on a cloud system, and then you're moving on to MapReduce. What are the sort of main features when it comes to data locality? Does the workflow know about that, or does it sort of say, I don't want to know about that, move it on to
It depends. So by the way, I didn't develop these tools. I just used them and tested them. But these are highly configurable to take locality aspects into account, both with respect to data processing, but also to start programs only on that nodes where the right environment is available.
I was wondering about the various distributed computing topics that you've been working on, like from climate change to particle physics to possibly genetics. So those are like very diverse, very interesting application fields. And how far can you use the same computing methods for all those fields, or is there like also some adaptation necessary in terms of the kind of computing that they require in terms of the distribution?
Well, so if you talk about MapReduce, for example, then in principle this framework is very generic, but we have seen we then face problems if we want to use this C++ code, for example. So this is then where it's not generic enough. But in principle, the ideas behind this, these are always the same, but of course, then when it comes to do the actual kind of analysis, then you need the domain knowledge, where you then need the people from the particular domain to do the actual analysis. I can just provide the distribution techniques around, but these are pretty universal.
One aspect, Helmut, your work in standardization groups.
Yes.
And I know from previous experience how important it is. Will you continue to contribute in standardization, or?
Well, I stopped doing so when I then here went to Iceland. in principle, they even pay you for working in these, so the funding is not the problem, but it's rather the traveling that it can be annoying if you are located in Germany. It's just a 1 hour flight to to south of France, where Etsy is located. Here in Iceland, it's almost then just a whole day that you spend in traveling. This is the reason why I did not work in this field recently. But it's definitely a very interesting experience.
Because of networking? Or?
Networking, but also to learn how standards are made, which compromises because of industry interests have to be made. And yes, political interests. Yes.
Right. Any more? I think we will stop with the story that you told me when you arrived in Iceland in 2008. You were told, or you learned from the hot tub in Vesturbæjarlaug that this was a time of crisis in Iceland, and as a measure of how not significant this crisis was, you were an example of hope, because people thought if somebody from Germany is taking up an academic post in Iceland, maybe the situation is not as grim as we were told. And I don't know if it was because of your your arrival, but we're certainly getting out of it. And with that, I think I would like to applaud you and thank you for your lecture. We hand you over this and invite you and the company to join us for a brief outside and continue the discussion on lighter notes. And again, congratulations and thank you for being with us and take part in building this talented team in IVT.
Yes, thank you for providing this excellent environment here.